Hello class and thank you for watching the second part of 5.1 quadratic functions. In this second part, we're going to go over quadratic functions written in polynomial form. So let's begin by first writing what the polynomial form of a quadratic function looks like. So it would be the format of a times x to the second power plus b times x plus c. So in this format, we're not given again the horizontal and vertical shift and identifying what the vertex is. So this right here, like I said, is the polynomial form of our quadratic. Some books will refer to this as the standard form. I really don't like referring to this as a standard form because the standard form to me, again, tells me how it transforms the original function of x squared using horizontal and vertical shifts along with vertical dilations. This one right here just simply identifies my terms in polynomial form because we have a quadratic term, a linear term, and my constant. So I refer to it more as polynomial. Well, and while in other, like I mentioned, in some books they'll refer to this as standard form. But for my purposes for this instruction, we're going to just call it polynomial form. Now, even though the polynomial form doesn't identify the vertex, we can identify it. We can calculate what the vertex is of this without having to actually graph it by using the following. Now, the x-coordinate of the vertex is equivalent to negative b divided by 2a, where the b and a value come from the equation itself, from this format right there. So the x-coordinate of the vertex is calculated by getting the opposite of the b value or multiplying the b with -1 and dividing that answer by the product of 2 times a. Now the way we figure out the y-coordinate is by substituting in. This notation means that we're going to substitute in the x-coordinate into the parabolas equation and evaluate the function at that x value, at whatever x value we get right there. So let's look at an example. Let's jump right in and let's look at an example of how we can use this equation and graph this equation without using a graphing device. So first we're going to figure out the x-coordinate of the vertex. I'm going to call it h, okay? Since the vertex form of the parabola is, let me get a thinner marker, a times x minus h to the second power plus k. I'm going to identify what the vertex is. Again, these two values here. So I'm going to call them h and k. H for the horizontal shift and k for the vertical shift. So how do we do this? Well, the formula to find the value of h is to simply get -1 multiplied with the value of b and divided by 2 times the value of a. So in this example, since it's in polynomial form, a would be this number here at the beginning. This would be a, and b would be this number of -4. So we're going to substitute those numbers into this formula. So we have -1 times my b value of -4 divided by 2 times the value of a. So simplifying this gives me 4 over 2, which is 2. So that is the horizontal shift, okay? So the h value, the horizontal shift, is going to be 2 units to the right. Since it's positive, it's going to move to the right 2. Now to figure out the vertical shift, k, all we're going to do is replace the x values. So we have 1 times x to the second power minus 4 times x minus 5. So to find the value of k, we're going to now substitute in this number 2 into the equation. So we have 1 times 2 to the second power minus 4 times 2 minus 5. And then simplifying this, we're going to end up with the following. We're going to end up with 4 in the first term, minus 8 in the second term, minus 5 on the, we're just going to bring down the minus 5. And then from left to right, we end up with -4 minus 5, which is -9. So the vertex here will have an x value of 2. So let's jump into example number 4a. So here we're going to graph the quadratic in its polynomial form. So what we're going to use again is identify what the vertex is. If we know where the vertex is, again, we can then find points again that are going to make things easier to identify because we know the vertex is in the center of the parabola. So to identify, because the vertex form, just so you understand the variables I'm using, is in the format of this, okay, where our horizontal shift and our vertical shift identify the new location of this vertex, I'm going to call h again, the x coordinate of the vertex. So instead of using the letters x and y, I'm going to use the letters h and k to identify the x and y coordinates of the vertex. Beginning with h, the formula to figure out the x coordinate of the vertex, we're going to get negative b, which is negative 1 times b, and divided by 2 times a. And the values of a, b, and c again come from the quadratic equation, or the quadratic, this polynomial form, where the value of a is going to be this number right here, which is a 1, and the value of b is the negative 4. So substituting those values in here, we end up with negative 1 times negative 4 divided by 2 times the value of a. So we have positive 4 divided by 2, which simplifies to 2. Now to figure out the vertical shift, again the y coordinate of the vertex, we're now going to plug in this number 2 into the x values of the function. So since the function is 1 times x to the second power minus 4 times x minus 5, plugging in the number 2 in there, we're going to get the following. We're going to end up with a total of negative 9, I believe. Well, let's simplify. There's going to be 2 to the second power, which is 4 times 1, which is 4. This multiplies to give me 8 and minus 5. Well, yep, it ends up equaling to a total of negative 9. So the vertex of our parabola is at 2 and negative 9. So 2, negative 9 is all the way down there, which means that again, that there's this imaginary vertical line that cuts the parabola into 2 equal parts, again, my axis of symmetry. And because of that, I just need to identify one point either to the left or to the right of the axis of symmetry, and the parabola again is going to be symmetrical and it's going to draw itself on the other side. So here, let's figure out the y-intercept. In the quadratic form, the y-intercept is the easiest thing in the polynomial form. In the polynomial form, the y-intercept is the easiest thing to identify on this thing because all we need to do is plug in the number 0. So if I evaluate my function at 0, notice that the first term has an x, so 0 to the second power minus 4 times 0 minus 5. And because these numbers are being multiplied with 0, we end up with 0, 0, and minus 5. So we just simply end up again with the constant because that's the only thing that didn't get eliminated or multiplied with 0. And then adding 0 throughout the entire thing just leaves me again with the constant of negative 5. So I'm going to cross the y-axis at negative 5. So let me plot that second point on our graph. So here we have that one. And because of symmetry, this is what the left side looks like. The right side, again, is going to be symmetrical and it's going to look exactly the same way. So the parabola will look like this. Now, the more points I have, the more accurate the graph is going to look like. But again, finding these 2 points, especially with your assignment online, just plotting again the vertex and any one of these 2 points on the left and right will draw the rest of the parabola by itself. So let's try it. Let's now try a second example. So here we have this function here. So let's figure out what the vertex is by first figuring out the x coordinate of the vertex, which remember I'm calling h. So we're going to get negative 1 times the value of b and divided by 2 times the value of a. So here our value of b is 6, so negative 1 times 6 divided by 2 times the value of a. Our value of a here is negative 1. So we're going to end up with negative 6 divided by negative 2, which is 3. Now to figure out the y value of the vertex, which I'm calling k, we're going to now substitute in that 3 into the quadratic function. So we end up with negative 9, 18, and minus 8. So this simplifies to 9, and 9 minus 8 is 1. Sorry about that. So our vertex is at 3 and 1. So 3 and 1. Right there. And let's figure out what another point is. Well, let me just draw my axis of symmetry, which is going to be this vertical line here, just so I know where the symmetry is. And I just need another point. And like I said, the easiest point in this type of situation when we're given the quadratic in this format is to find the y-intercept. So f of 0 will simply be -8, the constant. So the parabola opens like this, and because of symmetry, to the right of our parabola, it was going to look like that. So there, we have drawn the graph to this quadratic equation. Okay, so now let's look at, without graphing, let's identify the key characteristics to these quadratic equations again. So without using a graphing calculator to graph this and identify these things, let's do this again arithmetically, so algebraically. So algebraically, to find the vertex, we need again the two values. We need the h value, again the x coordinate of the vertex, and the k value, the y coordinate of the vertex. So let's start with the h value. So we're going to get -1 times the value of b, which right here is -8, and divided by 2 times the value of a, which is 1. So this is going to simplify to 8 divided by 2, which is 4. So now to figure out the k value, or the y value of the vertex, we're going to now plug in this number 4 into our quadratic function. Now this simplifies to the number -1, and now we have our vertex. So the vertex is 4, -1, which means that the axis of symmetry is going to be x equals +4. Now we need the x-intercept and the y-intercept. Might as well find the y-intercept also. Our y-intercept is going to be 0, 15, because remember, all we have to do to figure out the y-intercept is plug in the number 0 in for x, and in this format it just simply cancels these terms out and gives you that value there. So we have our vertex, our axis of symmetry, and the y-intercept. The only thing left to find is the x-intercept. Well, just like with the quadratic form, the vertex form of the quadratic, the polynomial form, or this form of the quadratic, requires us to do the exact same thing. Figure out the values of x where the quadratic is going to equal to 0. So to find our x-intercept, we're going to set up an equation. So we're going to get our quadratic and set it equal to 0. Now for this particular quadratic form, we can do by using inverse operation. We're moving the 15 to the other side and things like that. This requires, again, because it's in the polynomial form, it needs to be solved by using factorization. So we're going to break this apart into the linear factors. So we have x and x. That's how we break up our x squared. So x and x. Since this sign right here is negative, that means the larger factor of the 15 that we're going to focus on right now is going to be negative. And since a negative times a positive is negative, that means that the smaller factor of this 15 we're going to factor right now also has to be negative. Now to break down 15. So the factors for 15 have several options. We can do 1 times 15, 3 times 5, 5 times 3, which is the same thing, and 15 times 1, which is the same thing. So we have these two options to choose from. Now the option that we want is, we want to get, again, by trial and error, we want to get the numbers to add up to a -8. So if I try 15 and 1, that doesn't work out, because a -15 plus a -1 equals -16. So that's not the set that I want. So I want to use the second set. So I want to use a +5 and a +3. Or 5 and 3, not positive, but 5 and 3. So -5 plus -3 does equal to the -8 that we want to match up in the middle. So with that factorization complete, then we have our x-intercept. So to solve the equation for the first one, so we have two options here. So x minus 5 is either equal to 0 or x minus 3 equals to 0, which means that the equations are either +5 or x equals to +3. So these are x-intercepts. And there we found all the key characteristics to our quadratic. We know where the vertex is, we know where the axis of symmetry is, we know our y-intercept, and the two places we're going to cross the x-axis. So let's go over another example. Here we have example B, and we want to identify yet again the same four things. So here, let's start by first figuring out the vertex. So we're going to get what's this? So let me get a nice pen. 3, let's do 3. Yeah, much better. Okay, so let's figure out the h value. So we're going to get -1 times the value of b, which in this case is -1, and divided by 2 times the value of a, which is +1. So we end up with a +1 on top, we end up with 2 on the bottom, and that just equals to the decimal value of 0.5, which I'm going to keep it as a fraction of 1/2. Now to figure out the k value, I'm not going to use that number and plug it into my x. So we have x squared minus 1 times x minus 30. So we have 1/2, 1/2. Or if you want to use the decimal value, you're more than welcome to use the decimal value of 0.5 if you're not fitting again the fraction of 1/2. And this equals to a total of -30.25, which is -121 divided by 4. There we go. So there is our vertex, which means that the axis of symmetry is the vertical line of x equals 1/2, and the y-intercept is 0 and -30. So it's easy to see, identify the y-intercept for these problems, because it's just simply, again, the constant that we have right there. Now, lastly, the x-intercept. When we're going to cross the x-axis. So we're going to end up having to solve the following equation. So we're going to get our quadratic and set it equal to 0. And again, just to remind you, the way that we solve this equation is not by doing inverse operations. We have to first get the linear factors to our quadratic. So we have to break this up. So this is x and x. Negative, negative, negative is positive. And now the factors of 30. So we have several options again. 1 and 30. We have 2 and 15. We have 3 and 10, 4, 5 and 6, and then 6 and 5, 10 and 3, 15, 2, and 30 and 1. Okay, so now we want again to use numbers that, because the signs are different, as you see right here, that give me a 1 right there. So let's try, I'm just going to randomly pick this one right here, 10 and 3. So 10 and 3. Since 10 is bigger, it goes in the front, and 3 is smaller, so it goes there. So right here, this doesn't work because a -10 plus a +3, that gives us a total of -7. And we want a negative value, but a -1. So that can't work out. So let's try the last example right there. So let's put 6 again, and the order is going to be 6 first because 6 is bigger and 5 is smaller. So -6 plus a +5, that does equal to -1. So that's the combination that we want to use. So we don't need this one. And we're going to use the last one. So 6 and 5. So since we're multiplying these two things and we want the answer to be 0, that either means that x minus 6 is going to give us that 0, or the x plus 5 is going to end up equaling to 0. And since we don't know which one's going to be, we're using that, again, inclusive OR. So we have two places where it's going to cross the x-axis. X is going to cross the x-axis at +6, and we're going to cross the x-axis at -5. So those are the x-intercepts. my y-intercept, my vertex, and my axis of symmetry. Let's now look at example C. For example C, let's figure out the x coordinate of the vertex. So again, the formula to do that is -1 times the value of b, which in this case is -16, and we want to divide that by 2 times the value of a, which is +3. So we're going to end up with +16 divided by 2 times 3 is 6. And that fraction reduces because it's divisible by, we can leave it like that, but since it's a common factor of 2, 8/3. Now to identify the y coordinate of the vertex, we're now going to plug in that number into our quadratic function. Now I'm not going to bother just doing the math. I'm just going to plug this into my calculator, and I'm going to end up with the decimal value of -0.333 that repeats, which in fraction form is -1/3. So we have our vertex. So the center of our quadratic is at 8/3, and the y value is -1/3. That means that our axis of symmetry is the vertical line x equals 8/3. And the y-intercept here, when x is equal to 0, the y value will be 21. So we're not across the y-axis all the way up 21 units. Now for the fun part, for the x-intercept. So here, we're simply going to get our quadratic function and set it equal to 0 and find out where we're going to cross the x-axis. Now we can, because it's a quadratic and we can identify these things again from the graph, which we can just simply use decimals, but if we do that, like, what's the fun in that, okay? So let's go through the procedure of how we factor this, and it's a good way, again, of building that skill of factorization. So for this particular problem, we're going to break up the problem the exact same way, okay? So we're going to start by writing x and x, so our linear factors. We want to set it equal to 0. And since the middle sign is negative, that means that this is going to be negative. And since a negative times a positive is negative, that means that the second factor is going to be negative. Now, but this particular problem, because our leading coefficient is not 1, we have something else that's not 1. We're going to multiply all of these two quantities together. So we're going to multiply the 3 with the 21. And that's going to give us a total of 63. Sorry, 3 times 21, which is 63. And that's what we want to find the factors of. We want to find the factors of 63 this time and not 21. So 1 and 63 is an option. 2 doesn't work because 63 is an odd number. 3 and 21 obviously works because that's the number we just used. 4 doesn't work. 5 tampoco. 6 doesn't work because 2 doesn't work. 6 doesn't work. In order for 6 to be a factor, that means 2 and 3 would have to be a factor. That 63 would be divisible by both 2 and 3. So 63 divided by 6 doesn't work. 63 can be divided by 7. So that means that if I multiply, sorry, that should be a 3. With 7, 7 times 9 is equal to 63. 8 obviously doesn't work, and 9, well, 9's already on the list. So this is the entire list that we have for the factors of 63. From that list, the one that we're going to use is going to be the last one. This one doesn't work, and neither does this one, but the last one will. So if I use a 9, put that in the front, and 7 on the back, this does gives me the -16 that I want in the middle. -9 plus -7 equals -16. So that's the combination I want to use. Now, because we multiplied the 21 by 3 to get that 63, we have to undo that. So we're going to divide both of these numbers by 3, by this quantity at the beginning. And we have the following factors. We have x minus 3 and x minus 7 over 3, since this doesn't divide out to a whole number, but it gives you my decimal, so I'm going to leave it as a fraction. Now the procedure is still going to be the same. So either x minus 3 is equal to 0, or x minus 7 over 3 has to equal to 0. So solving the first equation, moving the 3 to the other side will make it positive, and moving the fraction to the other side again will make it positive. So the answers are going to be positive 3 and positive 7 over 3. So this is where we're crossing the x-axis. And those are your x-intercepts. Okay, one more example of this here. We have now example D. So example 5D here. And let's identify again the vertex first. So H will be -1 times the B value of 36 divided by 2 times the A value of 7. And 36 divided by 14, that has a common factor of 2, so we could end up with -18 over 7. This, I don't recommend to use the decimal format of this one, because the decimal format would be 2.571428, and then it starts to repeat itself. 571428, 571428, and so on and so on. So you have that number that gets repeated over and over again. So I'm not going to use that. I'm going to use again instead the fraction. So the k value here would be 7 times this -18 over 7 to the second power plus 36 times -18 over 7 plus 5. Okay, and we get the following. I forgot to put the negative sign on this one. This should be negative that decimal value, all right? So we get the following. We get, and as a fraction, we end up with -289 over 7. And again, I'm just using my calculator just to plug it in my decimals calculator to plug that number in and have the calculator evaluate it for me, okay? So I'm not using the graphing utility, so I could just graph it. I'm doing again this by hand, but you can more than welcome to use the decimals calculator or any calculator to do the calculation from that point on. The one thing I don't want you to do is just graph it, plug this into a graphing utility calculator, and identifying again these things just by picking them from the graph. I want you to again to do the math to get these values. You can go back and check afterwards and check that your numbers are correct. I have no problem with that, as long as you don't initially just go straight into any graphing utility and just graph it and get the vertex from the graph. So there's our axis, our vertex, and our y-intercept. When x is equal to 0, we end up with just the value of 5. Now finally the fun part. How do we figure out the x-intercepts? So just again, we simply get our quadratic equation and equal it to 0. And we're going to solve this equation. So because it's a quadratic trinomial, we're going to break it up into its linear factors. So x plus, and we're going to multiply this leading term with the constant, which is going to be 35. So 7 times 5 is 35. And we're looking for the factors of 35. So 1 and 35, 2, no, 3, 4, 5, 7. And well, 5 times 7, 5 times 7, and then 7 times 5. So 5 and 7 do not work because we still need these numbers when I plug them in here to give me this number right here in the middle. So 5 and 7 doesn't work, but 1 and 35 do work. So 35 and 1 do work. And now what I'm going to do is I'm going to now divide by this number. Since that's the number in the beginning, that's the number we divide these values by. So I'm going to divide 35 by 7 and 1 divided by 7. The first fraction does reduce. 35 divided by 7 does give me 5. But the second fraction does not. 1 over 7 is going to stay as 1 over 7 since it gives you some decimal value. So our solutions are going to be the following. Either x plus 5 equals 0 or x plus 1 over 7 equals 0. And the opposite of adding 5 is subtracting 5. So 0 minus 5 is negative 5. And the same thing with the second equation, x plus 1 over 7 equals 0. The opposite of adding 1 over 7 is subtracting 1 over 7. So our x-intercepts are going to be the following. So we're crossing the x-axis at those two locations. Here's the y-intercept and your other values as well. Okay, let's now talk about minimum and maximum values to a parabola. And let's apply this again to some real-world scenarios that involve quadratics. So let's recap. So first of all, recall that the polynomial form of a quadratic is a times x squared plus bx plus c. Now this value of a tells me some important information about the quadratic. It tells me if it's going to have a maximum or minimum value. If the value of a is positive, then the parabola is going to open upwards, so it opens up, and the function f of x is going to have a minimum that's going to occur at, again, negative b divided by 2a. And the minimum value, again, is the y value of the vertex, which again that we've been practicing is f of negative b divided by 2a. Plugging in whatever this coordinate is, again, whatever this x value is, into the function and figuring out what the y value is. Now, if the value of a is negative, then what that tells me about the parabola is that the parabola opens down, and f is going to have a max at that location at x equals negative b divided by 2a. And the maximum value, again, is determined by substituting that number in to the function and figuring out what the output value is. Now, in each case, the x gives you the location of the maximum or minimum value, and the value of y identifies what that maximum or minimum value equals. So let's look at an example before we apply it to a real-world scenario. So something, again, abstract using this terminology. So let's obtain the information about the quadratic without using a graphing utility. So let's determine whether this is going to, again, have a max or a min. Well, the equation f of x equals negative 3x squared plus 6x minus 13. Since the value of a, again, is negative, that means that the parabola is going to open downwards like this. So the vertex is going to be the highest point. So this function, f of x, has an absolute max. This thing will have a maximum value. There will be no minimum because the graph is going to continue getting decreasing and decreasing from ends, but there will be a maximum point, which is where the vertex is located at. Now, to identify the location of the maximum, what we're going to do is simply do the same thing that we did in the previous examples. Figure out the h value, okay, by using negative b divided by 2a. So negative 1 times our b value, which in this case is 6, divided by 2 times our a value, which is negative 3. That's going to give us a total of negative 6 divided by negative 6, which is positive 1. So this is where the axis of symmetry is located, and this is where the maximum is going to occur. Now, to identify what the value of the maximum is, we're going to now plug that number in to the function. Okay, let's now identify what the maximum value actually is. Okay, so not a minimum. Oh, so not a minimum, and let's identify what the maximum value is. So what we're going to do is our quadratic, let me just write this down, is going to be replaced, our input value in our quadratic is replaced with 1. So since the maximum occurs at x equals 1, we're going to find it by simply substituting the value of 1 into x, just like we did on the previous examples in figuring out what the vertical shift is and identifying the vertical shift of the vertex. So here, plugging in -1, this is going to end up simplifying to a total of -10. Like I said, I just plugged it into my Desmos calculator to do the arithmetic. And there is my max. So the largest y value is -10. So that is the maximum value. Now, well, how is that identifying the domain and range? Well, the domain doesn't change, okay, because it's a quadratic equation. The domain is not interesting. It's going to be all real numbers. The interesting part here is the range. Because we have a maximum value, again, a maximum value here, all of my y values are going to be lower than this value right there, this maximum value of -10. So the range of this quadratic equation will be all of the y values that are going to be less than or equal to -10. That's going to be your range. And like I said, the domain is not interesting because it's a quadratic. The domain is going to be all real numbers. So that is not going to be affected at all on any of these examples when we shift and do any type of vertical or horizontal shift. The domain stays the same. But our range, however, is interesting, that it will be all the y values less, in this situation, less than -10, because -10 is going to be the highest point. It's going to be the max. Okay, so now let's look at some examples and let's apply this against some real world applications. Now, in the first example I have, I'm going to maximize revenue. So Concert Venue knows that if they charge $40 per ticket, they can sell 1,500 tickets. Now, for every $1 they increase the price, they sell 20 fewer tickets. That should not have a dollar sign in front of it. Now, what price should they charge to maximize their revenue? So let's see. Right now, $40 again. And if they add $1 for every ticket, then their ticket prices is going to go down. So this is what the prices is, and the number of tickets that they sell would be 1,500 minus 20 for every ticket that's going to increase. Okay, so if I add $1 per ticket, my price goes up. But if I add $1 every ticket, I go down by 20 tickets. So right here, to figure out what the quadratic function would be, I would multiply these two quantities, and we end up that the function that represents what's the price, what should they charge to maximum the price would be the following. So let's see, let's multiply these quantities. So we have the $40 plus $1 increase per ticket multiplied with the 1,500 tickets minus 20 tickets per ticket. And that's going to give us the following quadratic. -20x squared plus 700x plus 600. I'm sorry, 6,000. Okay, so this is the quadratic that we need to use. Now on the homework assignment, you won't have to, again, figure this out. I'll provide, again, the quadratic already in its polynomial form. You just need to figure out now what price should they charge in order to maximize their profit. Well, first of all, we know we are going to have a max. Since the value of A, again, is negative, we know that there has to be a maximum. Since it's a quadratic, the polynomial will look like this, and there has to be a maximum point there. Well, what is that value going to be? Well, first we have to figure out what the coordinate is for the x coordinate for this. So we first have to figure out how many tickets they must sell in order to get this max. So we're going to get negative 1 times b and divided by 2a. So from the formula, our b value was 700. So negative 1 times 700 divided by 2 times the value of a, which is negative 20. So negative 700 divided by negative 40. That simplifies to a total of 17.5 tickets. So let's say 18. They have to sell 18 tickets because obviously they cannot sell half of a ticket. So to maximize the profit, they would have to sell no more or less than 18 tickets. So now let's see what that maximum value is going to be. So we have y, we're going to plug in that 18 into the function. So negative 20 times 18 squared plus 700 times 18 plus the 6,000. So this ends up equaling to a total of $12,120. So if they sell 18 tickets, again, this is how much money they end up doing. Considering again that every time they increase the amounts by by a dollar, that it's going to decrease the value, the number of tickets that they sell. So the price that they should charge, sorry, not number of tickets, the price that they should charge should be $18 more. So we're talking about a total of $58. So they should increase the price to a total of $58. So they should add $18 to the price of 40, and that's going to maximize their profit to $12,120. Now let's look at an example where we're minimizing costs. So a student is designing a rectangular pen for their pet lizard. Now they want the length to be 5 feet longer than the width, and they have 20 feet of non-slip material to line the perimeter of the pen. Now they found that the cost of the material for the base and walls is a function of the pen's width, which is given by this equation, this quadratic equation here, where W is the width in feet. What width will minimize the cost of material? So let's see again this. So to figure out what's, again, first of all, what the minima, the smallest, the minimal cost is, we first have to figure out what that is going to be. What's the width that's going to result in the minimum cost? So we're going to get negative 1 times the value of b and divided by 2a. That's how we're going to figure out that first. So our b value is negative 20. 2 times our a value is 2. We're going to get with 20 divided by 4, which is equal to 5. So the width of the perimeter of this thing, of this rectangular shape, has to be 5. Okay, so we want this to be a width of 5. Now to figure out now that we know that, we can now figure out what the minimum cost is by evaluating the cost function with the number 5. Okay, so this ends up equaling to a total of 20. So it's going to cost him $20 if he makes the base of this pen 5 and the width 10. Maybe I should do it the other way around. 5, so it could be a little kind of scale, 10. Because we want the length to be 5 feet longer than the width. So if the width is equal to 5, that will make the length equal to 10. And that's going to minimize again how much it's going to cost him. It'll only cost him $20 if he makes the dimensions of the pen for his pet lizard a 5 by 10 rectangular pen. So the lining around there won't cost him too much. If he does any other, it might increase again the price. This would be the minimum price for such a thing. Okay, well that concludes the second part to 5.1 quadratic functions. I hope you found these video notes helpful, and like always, I appreciate you watching and I hope you have a great day. Goodbye.